Good morning and welcome to this following lecture on sound and structural vibration. We are looking at a panel vibrating with a backed cavity. Okay, and last time I showed you this schematic here. So we will look at the problem that Kim and Brennan have solved. So there is a box. The top cover is actually a vibrating plate with simple support conditions here. Okay, and then it's backed by this rigid cavity. The other 5 walls are rigid. So one is you will have a 0.4 force excitation from the panel. So we'll look at vibration and sound. Similarly, we'll excite it with an acoustic speaker and again look at vibration and sound, and the paper describes theory and an experiment. Okay, so I will now show you the paper. So this is the paper here, published in Journal of Sound and Vibration 99, volume 223, number 1, pages 97 to 113, and the full title: Compact Matrix Formulation Using the Impedance and Mobility Approach for the Analysis of Structural Acoustic Systems. Okay, so let me move down. So this is the initial mobility and impedance part that I have described. You should be able to read the paper now. Then some initial definitions. Everything is here I have described in the lecture. So now they go to an example. This is the example. Okay, so there is this box now. Top cover is flexible, vibrates. Other walls are rigid, and it can be driven by a point force using an electromagnetic shaker. And this wall can be there's a speaker mounted that can drive the acoustic space. Okay, so L1, L2 and L3 are the dimensions. So this describes the experimental setup, and the parameter values: air density, phase speed, and the box is aluminum, or the vibrating panel is aluminum. The rest of the box is wooden, but the vibrating part is aluminum, and these are the values taken for the aluminum portion. And these of course are the uncoupled resonances, and the CNM values is very important. Okay, here are the plate uncoupled resonances: mode 1-1, 2-1, 3-1, 4-1, 5-1, 6-1, and these are the uncoupled acoustic mode numbers and resonances. Okay, and these are the CNM values. These are the CNM values. I will speak more about this after this paper is done. Okay, these are very important. Okay, so now if you look at the velocity, this is the velocity response of the panel. Okay, so one line is theory, the other line is experiment, and this is the sound pressure. So this is for point force excitation. Okay, there is a location where a point force is given, and these are the values, and you can more or less see that these peaks come where you have panel resonance or acoustic resonance. Okay, these are resonances of the system, and because actually it is air, it's very lightly loaded, so the uncoupled resonances more or less remain. Okay, they don't change very much. The next is due to acoustic excitation. Okay, this is the sound pressure inside. Okay, for experimental acoustic excitation. Okay, A, acoustic response with limp masses placed on plate. A rigid wall condition was assumed in the simulations. B, acoustic response masses removed from the plate. Full coupling was assumed in the simulations. Okay, so this is the coupled response, okay, due to acoustic excitation. And again, these peaks you see are all the original resonances of the system. Okay, so air being light, more or less the uncoupled resonances hold. Okay, and these are the dimensions L1, L2, L3, and the thickness of the plate is 5 millimeters and so forth. So using the derivation I have presented and this paper, you should be able to get these results quite easily. Okay, now I move back to my iPad and move forward with the next portion of the lecture. Now we will continue with the same problem and get some insights now. The insights proceed as follows. Okay, so we have the acoustic amplitudes given by the set of equations. Okay, we can combine them in a matrix form. I get an identity matrix n cos n minus za c then we have y bar s c bar transpose I m cross m is equal to z a q by y s g. Okay, this is the system of equations. So A is n cross 1 and B is m cross 1. Okay, now we want to find the coupled natural frequencies. Coupled natural frequencies. That means the plate is influenced by the acoustic space, so its natural frequencies change, and the acoustic space is modified by the flexible ball and its natural frequencies change. So we want the coupled natural frequencies, okay, and the way is we set the forcing to 0, the right side forcing, external forcing functions set to 0. Okay, and we take the determinant of the remaining matrix. So we take the determinant of the matrix. As you know, in ZA in YS you have the frequency term, okay, so that generates a polynomial which will give you the frequencies. So we have determinant of I n cross n minus ZA C, then YS C transpose I m cross m. We take the determinant of this matrix and we set it to 0. That is what we do. Okay. Now, very interestingly, it turns out that this determinant, okay, this determinant is equal to, identically equal to the determinant of another matrix, which is I n cross n plus Z A C Y S C bar transpose. Okay, it's interesting. It's an interesting result. Also equal to the determinant of I m cross m plus Y S C transpose Z A C. Okay, it's interesting. So now that has to be set to 0 obviously, okay, and we will take this form, we will take the latter form, we will take this separate, this form and deal with it. Okay. Now, so suppose we consider m as equal to 3, that means 3 panel modes or 3 plate modes. Okay. It is an approximation, so we can consider as many modes in acoustics or panel as we want, okay, because you deal with the modal sum, you truncate somewhere, right. So you can consider as many as you want as a study to begin with. So we will take now n equal to 1, which is one acoustic mode, one acoustic mode. Okay. If we do that, then I am going to write this in here. So this determinant, okay, looks like this. It looks a little, I mean that matrix first of all looks like this. It looks like 1 plus j omega C11 squared rho 0 C0 squared A1 by rho, I can take it as structure or panel, let me write rho structure, thickness, area of that panel, volume of the space, omega p1 square minus omega square. Omega p1 is the first panel uncoupled resonance value. Okay. The 1 2 term in the matrix will be j omega C11 rho 0 C0 squared into C12 into A1 divided by again rho S H S F V omega P 1 square minus omega square. Okay, so you can see that this was C11 square, this is C11, C12, everything else is same. So you will have C11, C13 and all else is same. Okay, and in here the 1 will not be there, so you will have C11, C12. Okay, and all other constants and omega P2 square minus omega square and all other constants in the numerator, j omega rho 0 c0 square a1 etc. Okay, and here again you will have 1 plus j omega c22 square etc. Okay, in the here you will have 1 plus j omega one plus j omega c33 square okay, rho 0 c0 squared a1 by rho sh sf v omega p3 squared omega squared. Okay, I think this will be C12 squared and this will be C13 squared. We will check from the paper. 13 squared. Okay, now so this is a matrix, so there will be an element here, similarly there will be an element here similarly. So this is the matrix. Okay, now just remember the form of this matrix. This can be given by or written down as I 3 cross 3, an identity matrix 3 cross 3 dimension plus U1 into B1 transpose. Okay, so it can be written so simply. And what is U1? U1 is given by j omega c11 by rho s h sf into omega p1 square minus omega square j omega c12 divided by rho sh sf omega p2 square minus omega square, and the third term is j omega c13 by rho sh sf omega p3 square minus omega square transpose. Okay, we will consider it to be vertical. So U1 is 3 cos 1. Okay, or rather it's m cross 1. So the dimension is equal to number of panel modes, plate modes that we are considering. And U1 is related to structural properties, plate properties, structural properties. Okay, plate density, plate thickness, plate surface area, plate resonances. Okay, so you can see that plate resonance is related to structure. Okay, now let us look at V1. V1 is given by rho 0 C0 squared C11 A1 by V. The A's have been defined before. Okay, so rho 0 C0 squared C12 A1 by V, rho 0 C0 squared C13 A1 by V transpose. We will consider this also vertical. So V1, okay, V1 is also 3 cross 1. That means it agrees with U1. Okay, but it has all the acoustic properties, and the number of V's, how many V's will be there, the number of V vectors, that is Vi, whether 1 or 2 or 3, depends on number of acoustic modes considered. Number of acoustic modes. Okay, that's the structure. That means what? That complicated looking matrix first of all can be represented very easily like this, and U1 has structural properties, V1 carries acoustic cavity properties. Now even more interestingly, now if we are looking at the determinant of this, right? So determinant of now I33 is a 3 by 3 identity matrix. Okay, it looks like this: 1 0 0 0 1 0 0 0 1. That's I33. So we are looking for the determinant of this plus U1 transpose V1. Okay. Oh, sorry. Yeah, sorry. That would become a scalar. U1 into V1 transpose. Okay. And this determinant is 1 plus U1 transpose V1. That's all. Okay. So let me write that also. So how does it look? How does this look? Okay, this looks like this. It looks like 1 plus C11 square rho 0 C0 squared by rho S H S F V omega P1 squared minus omega squared plus C12 squared rho 0 C0 squared by rho S H S F V omega P2 squared minus omega squared plus C13 squared rho 0 C0 squared divided by rho S H S F V omega P3 squared minus omega squared. That is the determinant. We will set this to 0 to figure out my new solutions of omega, okay, later. Okay. Now, what would be the structure? What would be the structure if now we choose M equal to 3, that means 3 panel modes, and we choose N equal to 2, that is 2 acoustic modes. Okay. So, U's, there will be U, right, and the U will have M cross 1 dimensions, okay, and therefore the V's, okay, V's also will have M cross 1 dimension. But now how many U's and how many V's will be there, that is decided by the number of acoustic modes. So, I will run from 1 to 2, okay, and I call it the coupling matrix, okay. Let us give it a name, we will call it the coefficient. So, this matrix here that we have, we will give it a name, we will call it the coefficient coupling matrix, coefficient coupling matrix or coupling matrix. So, whenever I refer to that. So, how does this coupling matrix look like for this situation of 3 panel modes and 2 acoustic modes? It can be written as I, of course 3 comma 3 plus U1 V1 transpose plus U2 V2 transpose. That is how the matrix looks like, very simple, okay. Now, the next level is I want the determinant of this, okay. We have to compute the determinant of this matrix. And how does the determinant look? It approximately, not exactly, this was exact, till here it was exact, okay, but here how does the determinant look? It looks approximately like 1 plus U1 transpose V1 into 1 plus U2 transpose V2, okay. But what is it exactly? Exactly it is this product plus some extra terms. There are some extra terms, okay. These extra terms become negligible provided the fluid loading is low, that means fluid density is small compared to the plate density, okay. So, this approximation becomes better and better as the fluid density relative to plate density goes down, okay. Now, right now the time is up, so we will continue this discussion in the next class. Thanks.